Magnetic material are generally classified into three types based on the behavior of materials in a magnetizing field. They are diamagnetic, paramagnetic and ferromagnetic material, which are deal with in this session. There are three types of material. One is the diamagnetic, another one is the paramagnetic and ferromagnetic materials. First of all, we discuss about diamagnetic materials. What is mean by diamagnetic materials? The orbital motion of electrons around the nucleus produce a magnetic field perpendicular to the plane of the orbit. Thus, each electron orbit has finite orbital magnetic dipole moment. Since the orbital planes are oriented in random manner, the vector sum of magnetic moment is 0 and there is no resultant magnetic moment for each atom, because the atoms are moving in a random manner. Sum of the magnetic moment should be is 0 and there is no resultant magnetic momentum for each atom. In the presence of an external magnetic field, what happens? Some electrons are speeded up and some are slowed down. The electrons whose movements were antiparallel are speeded up according to Lenz's law. What is the concept of Lenz's law? Produce an induced magnetic moment in a direction opposite to the field. This is the concept of Lenz's law. Produces an induced magnetic moment in a direction opposite to the field. The induced moment disappears as soon as the external field is removed. It's a very important point. The induced moment disappears as soon as the external field is removed. Then the definition of diamagnetic material. When placed in the non-uniform magnetic field, what happens? The interaction between the induced magnetic moment and the external field creates a force which tends to move the material from stronger part to weaker part of the external field. This is a very, very important point. Stronger part to weaker part of the external field. When placed in a non-uniform magnetic field, the interaction between the induced magnetic moment and the external field creates a force which tends to move the material from stronger part to weaker part of the external field. It means that diamagnetic material is repelled by the field. Once again repeat, it means that diamagnetic material is repelled by the field. This action is called diamagnetic action and such materials are known as diamagnetic materials. This is a very, very important 2-mark question. Examples of diamagnetic material is nothing but bismuth, copper and water, etc. The properties of diamagnetic materials are. What are the properties of diamagnetic materials? First property, magnetic susceptibility is negative. So note it down, this point, 4 point. Magnetic susceptibility is negative. Second point, relative permeability is slightly less than unity. Third one, the magnetic field lines are repelled or expelled by diamagnetic materials when placed in a magnetic field. The last point, susceptibility is nearly temperature independent. So very, very important 4 points for the properties of diamagnetic material. Next, second one, paramagnetic materials. In some magnetic material, Each atom or molecule has net magnetic dipole moment, which is the vector sum of orbital and spin magnetic moment of electrons. Due to the random orientation of these magnetic moments, the net magnetic moment of the materials is 0. So, note it down this point. Due to the random orientation of these magnetic moments, the net magnetic moment of the materials is 0. So, next important point for the ferromagnetic material. What is meant by ferromagnetic material means, in the presence of external magnetic field, what happens? The torque acting on the atomic dipoles will align them in the field direction. So, torque acting on the atomic dipoles will align them in the field direction. As a result, there is net magnetic moment, dipole moment induced in the direction of the applied field. So, net magnetic dipole moment induced in the direction of the applied field. The induced dipole moment is present as long as external field exists. When placed in a non-uniform magnetic field, so if suppose the material paramagnetic material, when placed in a non-uniform magnetic field, the paramagnetic materials will have a tendency to move from weaker to stronger part of the field. So, last point here, stronger to weaker part. Here, this is the point. Diamagnetic material means external fields created a force which tends to move the material from stronger part to weaker part of the external field. Here, paramagnetic materials tendency to move from weaker to stronger part of the field. So, paramagnetic materials will have a tendency to move from weaker to stronger part of the field. Materials which exhibit weak magnetism in the direction of the applied field are known as paramagnetic materials. So, important point, please note it down. Materials which exhibit weak magnetism in the direction of the applied field are known as paramagnetic materials. Examples: aluminum, platinum and chromium, etc. This example very important for your objective type question. Aluminum, platinum and chromium are example of paramagnetic materials. Now, we should know the properties of paramagnetic materials. There are 4 points. Magnetic susceptibility is positive and small. The last diamagnetic material property, first point is magnetic susceptibility is negative. Here magnetic susceptibility is positive and small for the paramagnetic material. Second, relative permeability is greater than unity. So, last diamagnetic property, second point says relative permeability is slightly less than unity, here greater than unity. The magnetic field lines are attracted into the paramagnetic materials when placed in a magnetic field. The last one, susceptibility is inversely proportional to the temperature. Here susceptibility is nearly temperature independent. Then next important law, Curie's law. Curie's law state that when temperature is increased, thermal vibration will upset the alignment of magnetic dipole moments. Once again repeat, when temperature is increased, thermal vibration will upset the alignment of magnetic dipole moments. Therefore, the magnetic susceptibility decreases with increase in temperature. Please note it down, very important point. The magnetic susceptibility decreases with increase in temperature. In many cases, the susceptibility of the material is, this is a very, very important formula, psi m is inversely proportional to temperature. Psi m is equal to C by T. C, here C is the Curie constant. C is the Curie constant. So, psi m is equal to C by capital T. Once again repeat the law statement. Curie's law state that when temperature is increased, thermal vibration will upset the alignment of magnetic dipole moments. Therefore, the magnetic susceptibility decreases with increase in temperature. When temperature is increased, thermal vibration will upset the alignment of magnetic dipole moments. Therefore, the magnetic susceptibility decreases with increase in temperatures. This is the formula. Psi m is inversely proportional to T. When we remove the proportionality, we can multiply the proportionality constant. Psi m is equal to C divided by T. Here C is the called Curie constant and temperature T is in Kelvin. The graph drawn between magnetic susceptibility and temperature is shown in the figure, which is rectangular hyperbola. Rectangle. Here, this is the graph. When the temperature is increases, susceptibility is decrease. The next important material, ferromagnetic material. So here, an atom or a molecule in a ferromagnetic material possesses net magnetic dipole moment as in a paramagnetic material. A ferromagnetic material is made up of smaller region called ferromagnetic domain. Very, very important point, note it down. Ferromagnetic material is made up of smaller regions called ferromagnetic domain. Within each domain, the magnetic moments are spontaneously aligned in a direction. This alignment is caused by strong interaction arising from electron spin, which depends on the interatomic distance. Each domain has net magnetization in a directions. However, the direction of the magnetization varies from domain to domain and thus net magnetization of the specimen is 0. So, very important point here. However, the direction of the magnetization varies from domain to domain and thus net magnetization of the specimen is 0. In the presence of external magnetic field, two processes take place. What are the two processes? Very, very important two processes. First process is the domain having magnetic moment parallel to the field grow in size. So, domains having magnetic moments parallel to the field grow in size. The second point, the other domain not parallel to field are rotated so that they are aligned with the field. So, as a result of these mechanisms, there is a strong net magnetization of the material in the direction of the applied field. So, two important points. This is the first important point is the domain having magnetic moments parallel to the field grow in size. Second important point, the other domains not parallel to field are rotated so that they are aligned with the field. As a result of these mechanism, there is a strong net magnetization of the material in the direction of the applied field. So, this is the diagram for the domain. Unmagnetized iron nail, smaller domain, then magnet B, iron in the presence of magnetic field, C, a non-magnetic material. If suppose ferromagnetic material when placed in a non-uniform magnetic field. What happens? The ferromagnetic materials will have a strong tendency to move from weaker to strong part of the field. Materials which exhibit strong magnetism in the direction of the applied field are called ferromagnetic materials. Example, iron, nickel and cobalt. So once again repeat, what is meant by ferromagnetic material means when placed in a non-uniform magnetic field, the ferromagnetic materials will have a strong tendency to move from weaker to stronger part of the field. Materials which exhibit strong magnetism in the direction of applied field are called ferromagnetic materials. Example, iron, nickel and cobalt. Next important thing is properties of, we should know about the properties of ferromagnetic materials. First point, there are 4 points. Magnetic susceptibility is positive and large. Relative permeability is large. The magnetic field lines are strongly attracted into the ferromagnetic materials when placed in a magnetic field. The last one is susceptibility is inversely proportional to temperature. Then next, Curie-Weiss law. Curie-Weiss law. As the temperature increases, the ferromagnetism decreases due to the increasing thermal agitation of the atomic dipoles. So this is a very important point. Underline this point, note it down. At a particular temperature, ferromagnetic material becomes paramagnetic. This temperature is known as Curie temperature. So at a particular temperature, ferromagnetic material becomes paramagnetic. This temperature is known as Curie temperature. The susceptibility of the material above the Curie temperature is given by psi m is equal to C by T minus Tc. Here this is a formula for the ferromagnetic material. Psi m is equal to C divided by T minus Tc. This is a graph for the Curie-Weiss law. When the temperature is increases, then the ferromagnetic material becomes a paramagnetic material at particular temperature. Ferromagnetic material, it converted into paramagnetic material. This relation is called Curie-Weiss law. The constant C is called Curie constant and the temperature T is in Kelvin. A plot of magnetic susceptibility with the temperature is as shown in the figure. Then last one, important tabulation. Types of magnetism. Magnetic field is absent, magnetic field is present, magnetization of the material, susceptibility and relative permeability. This is a very important tabulation to know about the characteristics or properties of the dia, para and ferromagnetic material. So types of magnetism. Diamagnetism means magnetizing field is absent, H is equal to 0. Zero magnetic moment. Here this symbol is represent zero magnetic moment. For the paramagnetism, net magnetic moment but random alignment. This is the random alignment. This picture indicated the random alignment of the magnetizing field is absent. Then last one, for the ferromagnetism, net magnetic moment in a domain but random alignment of domain. The next important point, magnetizing field is present. First one is absent, second one is present means what happened? Alignment opposite to the field for the diamagnetism material. Alignment with the field for the paramagnetism material. Alignment with the field for the ferromagnetism material. Then magnetization of the material. This is a graph to indicate magnetization of the material. For the diamagnetism, this is the graph. Then for the paramagnetism, increasing order, then this is the positive and direction. This is also positive direction. This is the negative direction. Susceptibility should be negative for the diamagnetism. Then positive and small for the paramagnetism. Then Positive and large for the ferromagnetism. Susceptibility is negative for dia, positive and small for para, positive and large for ferromagnetism. Relative permeability, less than the unity, greater than unity, very large. This tabulation is very important to understand the behaviors or characteristics of diamagnetism and paramagnetism and ferromagnetism.